Hey Pre-Calc, we're ready for Pascal's triangle in section 9.7. And this is fun for me as a math, because this is actually starting to be a concept that's useful in both stats and calculus. So I imagine no matter where you go next year, whether it's stats, calculus, if you go off to college, you might use this in some way, shape, or form. And we've actually been alluding to this triangle before. And if you feel like it, you can pause the video and see if you can find a pattern from one number to the next. And if you want a suggestion before I tell you, the pink part is sort of helpful to see. And if you are ready for the answer, I'm about to just give it to you. How to create Pascal's triangle. So if you notice, it's a triangle where the outsides are all 1. So that's given to you. Well, to get the next number down, you add the two numbers, I guess, to the top left and the top right. So 1 plus 1 gives me 2. 1 plus 2 gives me 3. 1 plus 3 gives me 4. 1 plus 4 gives me 5. 3 plus 3 gives me 6. Now, I don't like how messy this picture gets. So I usually don't put those tick marks in there. But you can easily come up with the next row. I think you can. 1, 8, 28, 6, right? 56, 70, 56, 28, 8, and 1. Now there's a couple things that you should recognize. And first of all, the Pascal's triangle is symmetric. So what that means is the numbers, like if I drew a line down here, the numbers to the left are going to match up with the numbers on the right. The 4s, the 10s, the 15s, the 21s, 56. Now obviously the ones that go straight down the middle don't have repeats, and there's a reason for that. You should also notice that there's patterns if I went diagonally through this. You know, this one's counting by 1s. The next diagonal is counting by 2, then 3, then 4, then 5, then 6, then 7. You can continue that pattern down. And there's even patterns as I continue down, like this one's 3, then 6, and then 10. I think there's a pattern in here somewhere. It might be the second difference. But if you get bored at some point, you can Google Pascal's triangle, and you'll see a whole bunch of activities. But we're going to get to how this applies to what we're doing right now. And one thing I need to mention, I'll just scroll down, is these are actually called named by their rows. Now I know it's weird because we start with the 0th row, and there's a lot of reasons for that. And the main reason is anything to the 0 power is equal to 1. The next row is called the first row, and if you notice, if you were to expand these things, the coefficients match up perfectly. This is probably the one that you could probably do quickly in your head because you know to FOIL that. You know, x plus y times x plus y. You know, x times x is x squared. You'd have 2 xy's, and then y times y is y squared. And the reason why we have this pattern is because you probably don't want to do x plus y times x plus y times x plus y. Now, you might be saying, well, that would be pretty easy. All I'd have to do is FOIL these two, and then whatever I get there, I'd have to FOIL that to x plus y, and you'd be absolutely right. But I bet some of you would prefer a shortcut instead of doing that twice, but having to do it 6 times with very, very complicated things with x plus y to the 7th power. So here's your shortcut. Is the coefficients are 1, 7, 21, 35, 35, 21, 7, 1. And where did we get those numbers from? It is from the 7th row of Pascal's triangle. Now, the other piece that's really nice about this is you start with x to the 7th, and if you notice my second term, so this is my first term, my second term has x to the 6th in it, x to the 5th, x to the 4th, x to the third, x squared, x, and then no x. Now technically I could write x to the 0 power because x to the 0 power equals 1. But that's how you can tell that you're doing this correctly, that you have the right row and you have the right number of terms. I don't think I'm missing anything. So how do you determine y, the second term? I usually start at the end, y to the 7th, and then go backwards. But I've also seen students that don't write down y in the first term, and then they write y to the 1st in the second term, y squared in the third term, y to the 3rd in the 4th term. I'm losing count, so I think you can do that. Now I will practice that. Now before I do that, I want to point out, because this probably seems really new to you, and you might be sitting there and saying, how in the world did that how does that have anything to do with combinations or permutations? Well, if I asked you to do 7C0, now remember the first number needs to be bigger or equal to this last number, and as a reminder, this is 7 factorial over the difference factorial, the second number factorial. Well, everything cancels, I'm left with 1. Well, if I do 7C1, that's the first number factorial over the difference factorial times the second number factorial. And if you do the arithmetic, you'll see it's 7. So see if you think you know the next one already. And what you should recognize is these numbers are matching up perfectly to that row of Pascal's triangle. Which is part of the reason why I pointed out before that Pascal's triangle is symmetrical, and I've mentioned before to you in a previous video that 7C0 is equal to 7C7, 7C1 is equal to 7C6, 7C2 is equal to 7C5, and here as well. And you can work through the arithmetic on that. Yeah, I think I've said everything I wanted to about this. There's a lot of cool things about Pascal's triangle, but I'm trying to keep this video somewhat short and to the point, which I probably won't be able to do. So I'm giving you two options. You can do Pascal's triangle, you can do the binomial expansion. I should probably explain why it's called a binomial expansion, is because this is a binomial and it's a shortcut to other pieces. Now, if you're a fan of following this formula, which is pretty tough to read here, but hopefully it's readable on your page, sometimes what I'll do is I'll just make Pascal's triangle off to the side because it doesn't take that long, especially when you have a lot of practice with it. And I look at the exponent and I find the row, and I don't really count 0, 1, 2, 3, 4. I look at the second number. That's the row that we're in. So it's 1, 4, 6, 4, 1. And then you start with x to the 4th, x to the 3rd, x squared, x, and then there's no x over here. And then I like to start with y to the 4th over here, and then y cubed, y squared, y, and then no y, and then the only thing I'm missing now is putting some plus signs in here. And that's how you can quickly evaluate that piece. And we're done with that. Yeah, and then the next one, we're looking at 1, 5, 10, 10, 5, 1. So without having to do x plus y times x plus y times x plus y plus x plus y, you can quickly figure out that's going to be x to the 5th plus 5. And some people, when you get a lot of practice with this, you know without having to write out 1, 5, 10, 10, 5, 1. So I'm open either way that you do this, because then we have y to the 5th over here, y to the 4th. I didn't give myself much room here. Y cubed, y squared. Put in some pluses, and then we're good. And that is your answer for x plus y to the 5th. So as I move down, there's a little bit more tricks that you need to practice, and I want your answer in simplest form. So it's more complicated than just x plus y. We have 2x minus 1. Now remember, x and y are just variables. So as I go back, let me switch back to green because I did the green row 14641 because it is to the 4th power here. So let me write that out. Notice that I'm going to space things out a lot. And so we start out with the entire term of 2x to the 4th power. And if you're curious why I'm putting it in parentheses, it's because you have to take each piece, the 2 and the x to the 4th power. Up here, the only thing we were taking to the 4th power was x. 2x. Yep, I did something wrong, didn't I? And that's what I like about this math, is it's easy to tell when you made a mistake. Cubed, squared, 2x to the 1st, and then there's no 2x. So that's how I knew I made a mistake, because I was about to have a 2x over here, and I shouldn't have. Now what I like to do is put negative 1 to the 4th, and negative 1 to the 3rd, and negative 1 squared, and negative 1 to the 1st. And then there's no negative 1 here. And the reason why I like to do that is because it gives me the sign that I'm supposed to have for each term. So my first term, I shouldn't put a line there. Let me put it just, this is going to be my final answer. It's 2 to the 4th, 2, 4, 8, 16, x to the 4th. And every year I teach this, somebody does it wrong, so don't be that somebody. You have to do the exponent first. It's the order of operations. So 2 to the 3rd power first is 8. Times 4 is 32. Times negative 1 makes it negative 32 x to the 3rd. So then the next one, again, you have to do the exponents first. So 2 squared is 4. Negative 1 squared is positive 1. So we're looking at 4 times 6 is 24 times positive 1. It stays positive. So then the next one, you have to do the exponents. Well, 2 is not taken to a power, so that's fine. So we're looking at 8 times negative 1, because remember, a negative to an odd exponent stays negative. So we're looking at negative 8x. And negative 1 to the positive 4th power. It was weird that I said it that way, but we get positive 1. And this is our final answer. Now, again, every teacher is a little bit different. So you might hear a teacher say, whenever you have a negative here, I'll switch back to orange, your sign should alternate. And if you do the problem that way, you can disregard the negative to a power. I used to be a teacher that explained it that way, but I found more success telling students to leave it as negative 1. Because it's the same thing as adding negative 1. In my opinion, students that do it this way understand a little bit more. I think I'm going to end the video here, but before I end, I want to show you on a graphing calculator. So I'm going to pull up a graph of each of these. So I can only do this on, I couldn't do this with x and y, but I can do it here because I only have one variable. And all I want to show you is when I go to my table, I know they're equivalent if the y values are exactly the same everywhere. Uh-oh. Silly Mr. Higbee, I didn't double check that I typed this in correctly. I'm not going to go back and revise the video. You guys can laugh at me. That's fine. I accidentally put +2 here instead of +1. So now if I go back to my table, there we go. Now it's looking like it's exactly the same everywhere. So I know I did the problem correctly. And for the record, I did it correctly here. I just typed it incorrectly on my graph. So this is a good place to stop. And I will see you in the next video continuing exercise 4 and 5 and get you ready for the homework.